Hey guys, so in this one we are taking a look at exponentials. So exponentials are the things of this form: y equals a to the power x, where a is greater than 0, so it's positive, and not equal to 1. If we just had 1 to the power of x, every value for any value of x would just be 1, so it would just be a straight line. So a is positive and not equal to 1. Now we're also going to meet the special exponential function e to the power of x as well, and we're going to see why that's special. So exponentials have this really cool property that the bigger they are, the faster they change. So whether they are growing or decaying, the bigger they are, the faster their rate of change. So a good example here would be a population of rabbits. So the bigger a population of rabbits is, the faster they will reproduce, so the faster the rate of change of their population. So the bigger a population of rabbits, the faster their population will grow. Unless, of course, disease is spreading, in which case they will be decaying. Now, the bigger their population, the faster they would decay. So, let's look at the maths behind this then. First of all, we're going to have a look at an example function, and then at what the graph looks like. Okay, so our first example then is going to be y equals 2 to the power of x. So we're first of all going to fill in this table of values to see what happens, and then I'm going to tell you a very, very strange but awesome fact. So, when x is minus 3, we get 1 over 2 cubed, which is 1/8. And then we get 1 over 2 squared, which is 1/4. 1 over 2, which is 1/2. 2 to the power of 0 is 1. So we always get that value for any purely exponential function. When x is 0, any number to the power of 0 is 1. What do I mean by purely exponential function? Well, we're not multiplying a function or adding or subtracting anything to it. We're not transforming it in any way. So that's a common value to every exponential function. Then when x is 1, we've just got 2 to the power 1, which is 2. Then we got 2 squared, 4. 2 cubed, 8. 2 to the power 4, 16. 2 to the power 5, 32. So we can see things are starting to get quite big very, very quickly on the right hand side. In fact, they're getting very big at a faster rate. So all the way through this table, to get from value to value, we are multiplying by 2 each time. So it's getting twice as big from value to value. Now the very strange but awesome fact that I promised you was, if you fold a normal piece of paper in half 42 times, it would reach to the moon. Look it up if you don't believe me. Now the reason for that is we would be doubling the thickness of that piece of paper 42 times. Now it's impossible to do. You can only fold a piece of paper, I don't know, is it 8 times, maybe 10 times, something like that. But if you could fold a normal piece of paper in half 42 times, it would reach to the moon. It would be that thick. And that is because of exponential growth. So we can't do it, but if we could, it would reach to the moon. So what we're going to do now is take a look at the graph of this guy. Okay, so here's how our graph is going to look. Now this is representative really of all exponential graphs. On the next page we'll have a look at comparing two different values of a, but if ever you're asked to sketch these guys, something that looks like this would be absolutely fine as long as a is greater than 1. So, as I said on the previous page, all exponentials have that common value of y equals 1 when x is equal to 0. Any number to the power of 0 is just 1. So what's going on here? Well, on the left of x equals 0, so on the negative part of the x-axis, we are increasing, but because our values are fractional to the left, it doesn't seem as dramatic. But as soon as we are to the right of x equals 0, we're dealing now with whole numbers that are getting twice as big in this case because it's 2 to the power x. So we are dealing with numbers getting twice as big for every one that we go to the right. So the rate at which the function increases really kicks off, gets very dramatic. So what happens here, we can say first of all, as the value of x tends to infinity, so we can say that with a little arrow, so we would read that as x tends to infinity, the value of y shoots up also to infinity. So as x tends to infinity, y tends to infinity. So as x values get bigger, y values get bigger faster. Now, it's very important to realise as well, we never ever hit the x-axis. So y is never equal to 0. So in terms of our function, let's just generalise it. A to the power of x is never equal to 0. So 2 to the power x is never equal to 0. So too though are exponential functions never equal to 0. So what we can say on the left, as x tends to minus infinity, so as we keep going down to the left, as x tends to minus infinity, y tends to 0. So it will never hit 0, it will never hit the x-axis, because this exponential function can never be 0. But it can get closer and closer and closer and closer to 0, just never ever hit it. So now let's take a look at comparing 2 to the power of x to 10 to the power of x and see what our different value of a does. Okay then, so here we have a sketch of 10 to the power of x relative to 2 to the power of x. So what can we see here then? Well, what's happening on the left, 10 to the power of x gets smaller faster, and on the right it gets bigger faster, but it still goes through the same point on the y-axis. So what's with the difference in getting smaller and getting bigger? So we've got y equals 10 to the power of x. So on the left hand side, with 2 to the power x, we had 1/2, 1/4, 1/8. With 10 to the power of x, we're going to have 1/10, 1/100th, 1,000th, 1/10,000th. So these values are much smaller than for the values of 2 to the power of x. But on the right of 0, on the right of x equals 0, we've got 10, 100, 1000, 10,000, 100,000. So the values for the function are getting bigger much faster than they are for the value of y equals 2 to the power of x. So we get a steeper curve on the right and a steeper curve on the left too, because the values get smaller quicker and bigger quicker depending on which side of the y-axis you are on. In terms of a sketch though, again, if you're asked to sketch one of these, it's fine just to have a curve that gets close to the x-axis, goes through the y-axis at 1, and then speeds up in growth on the right. It's just nice to show you what happens with these guys relative to the size of A. Okay, now let's have a look at a value of A that is fractional, so it's between 0 and 1. So we're going for 1/2 to the power of x. Now when we got negative powers, they flip the fraction over. So 1/2 to the minus 3 is actually 8. 1/2 to the minus 2 is 4. 1/2 to the minus 1 is 2. 1/2 to the 0 is 1. 1/2 to the 1 is 1/2. 1/2 to the 2 is 1/4. Then we get 1/8, 1/16, and then 1/32. So you might notice something here. These values are almost the same as 2 to the power of x, except they are starting big and whole on the left. So when we have negative values, but then they're being divided by 2 as we move over to the right. So the graph is actually going to look like this. So it's a reflection of y equals 2 to the power of x through the y-axis. So it still goes through the y-axis at 1, but this time to the left of x equals 0 we get bigger, and this is because we have a fraction to a negative power, and on the right we get smaller because we have a fraction to a positive power. So the values to the right are all fractional, and they're getting twice as small with every one value that we go to the right, whereas on the left, with every value that we go to the left, our function is getting bigger because we've got a fraction to a negative value, which turns the fraction into a whole number. So what we can say here is as x tends to minus infinity, y tends to positive infinity, and on the right, as x tends to positive infinity, this time y tends to 0. So again, the exponential can never equal 0, but it can get really close to it, infinitely close. It can just never touch it. So this is what it looks like when we have a fractional value of a to the power of x. Okay, if we generalise here then and compare our graphs, so in blue we've got y equals a to the power of x when a is greater than 1. So that starts off small on the left and then grows exponentially as we move off to the right. Or in red, we've got y equals a to the x when a is between 0 and 1. So a is fractional. Now we can see that what we get is a reflection of each other. So why is that? Well, when a is fractional, we could say we've got 1 over a, which we could call a to the minus 1. So we've got y equals a to the minus 1 to the power of x. Now by the laws of indices, we could say that's y equals a to the minus x. So, if we think about this in terms of transformations, if we say on the right we've got f of x equals a to the power of x, we could say on the left that we've got f of minus x is a to the power of minus x. Now we know from our transformations of graphs that f of minus x is a reflection through the y-axis. So that's why we get a reflection of these curves through the y-axis. So y equals 1/2 to the power x and y equals 2 to the power x are reflections of each other through the y-axis, because one is f of minus x and one is f of x. Good times. Okay, now we're going to look at the special case. Okay, so the special case, y equals e to the power of x. Now, so far we've been looking at exponential functions. This guy is known as the exponential function. So, e is roughly equal to 2.72. It's known as Euler's constant. It was discovered by a very famous mathematician called Leonard Euler, who was actually investigating compound interest, and he came up with this constant, and it's actually one of the 5 most important numbers in maths. So these numbers, we've got 0, we've got 1, we've got pi, we've got I, which is the imaginary unit, it's the square root of -1, and we've got e. Now these 5 numbers are linked together to give us what's known as the beautiful equation, and they actually all play a part in the actual functions of trigonometry. So the actual maths that's going on behind the scenes when on your calculator you press sine, cos or tan. So very, very important stuff. Now, something that makes e so very special is that the gradient of e to the power of x anywhere on the curve of y equals e to the x is e to the x itself. So it's very, very important. The gradient of the function is the value of the function at that point. So we can go through examples of that. We do though, we're probably going to be seeing a lot in this chapter, functions of the form a times e to the power k times x. So here's a generalized sketch of this function. So we're multiplying the function by some value a. So the y-intercept is going to be a, whatever that is. So whatever we're multiplying the function by, that will be our y-intercept. Remember, the y-intercept of e to the power x would just be 1. So if we had a e to the x, it would be a. And then we got e to the power k times x. If k was negative, the graph would reflect through the y-axis. So that's just a good one to make a note of for now. Okay, so I decided to work in a sketch for y equals a e to the minus kx, which is just a reflection through the y-axis like that. Okay, so the last thing for this video that I highly recommend you take a note of is the gradient of different forms of the exponential function. So then we're also going to have a look at a few questions. So, the gradient of e to the power x is itself e to the power x. The gradient of e to the power kx is k times e to the power kx, and the gradient of a e to the power k times x is k times a e to the power k times x. So now we're going to have a look at using this info in some questions. Okay, so using the information we've just seen, we're going to find the gradient of whatever function we are given at the points that we're interested in, so the x values or the x coordinates, and we're going to give our answer in exact form. Now that just means to leave things in terms of e unless they work out nicely. So for our first function we got y equals e to the power x, and for part A we want the gradient at x equals 0. So we'll call it m. So m is just going to be e to the power of 0, which is 1. And then for b, we want the gradient at the point where x equals 5. Well, there, m is just e to the power 5. Good times. Question 2, we've got y equals e to the 7x. So what I'm going to do for this one is get a general expression for the gradient first. So we've got one on the form e to the power kx. So we know the gradient of that is k times e to the kx. So in general, the gradient is 7 e to the 7x. So now we've got 2 points, x equals 10. Well, m here would be 7 times e to the power 70. All we're doing is substituting in x equals 10 into 7e to the 7x. And then for part b, we got x equals minus 2. So m here would equal 7e to the minus 14. Now we could write that as 7 over e to the 14, like that. Last question, so this time we've got y equals 5e to the minus 3x. So again, I'm going to get a general expression for the gradient. So this time we have one on the form a e to the kx. So the k comes down and multiplies the a at the front. So in other words, we get minus 3 times 5, which is minus 15 e to the minus 3x. So first of all, we want the gradient at x equals minus 1. So that's going to be minus 15 e to the minus 3 times minus 1. So that's going to be to the positive 3. So minus 15 e to the 3. And then lastly, when x is equal to positive 3, m is going to be minus 15 e to the, well, minus 3 times 3 is minus 9. So we could write that as minus 15 over e to the power 9. Good times. Okay guys, that's it for exponentials. Next up, we're looking at logarithms. So excited.